All right, so welcome to Physics 2 for Engineers. I'm David. I'm going to be giving this study union review. The first thing I want to tell you is that the material we're going to use is available for you on this web page right here. If you go to it, there are 3 links here. The study union review, this is actually some scribbles that I'm going to be using to teach from. You probably don't want to see it. But this one, Study Union Review 2, that's the problems that we're going to do, and we also have the solutions for those problems. This way, if you are watching at home, you can follow along by pulling it up yourself, or if you need to review them more after we're finished, you can go back and look at anything you want. So the way I'm going to do this session is going to be about a 50-50 split. I'm probably going to pause briefly whenever the drilling starts. Bear with me. I'm going to briefly lecture on some material that you guys haven't seen in about 4 months, just so you remember what it is. And then we're going to do a problem. I'm going to give you an opportunity to solve the problem yourself. I strongly encourage you to give it a serious try. And then we will go over the problem after that, okay? So this is the website. But with that said, let's go ahead and get started. Okay? Okay, hold on. All right, so Physics 2 is the easiest class ever, because if you understand Physics 1, we only introduced one new thing in the entire semester, all right? And that new thing is charge, okay? So charge, which is measured in coulombs, is kind of like mass in that it's a real thing and that charges interact with other charges. However, it's a little different because there's no such thing as negative mass. We have a thing called positive charge and negative charge, and which one it is affects the way it behaves. So when we have positive charges, the force between them is going to repel, and when we have negative charges, the force between them is going to repel as well. When we have one of each, they attract each other, okay? So the very first thing that we look at in Physics 2 is we try to measure how strongly they attract or repel each other. This is called force, and the very first equation that we learn measures force. This is called Coulomb's law. F equals KQQ over R squared times the unit vector R hat. That's just a direction, okay? So this law should look really familiar because this law is basically the same thing as Newton's law for gravitation that we learned in Physics 1. The structure of the law is exactly the same, and that's not a coincidence. That should help you remember how the law works. Now, one of the things that we talk about in this class is the fact that these things are able to influence each other even when they don't touch each other. And so we ask ourselves, well, how on earth is that? That doesn't make any sense. Well, the next concept that we introduce is called electric field. And field is the answer for how particles influence each other without touching. The formula is very similar. It's KQ over R squared. The difference between force and field is that force is something that happens between 2 particles, and field is something that one particle does to a point in space, and it doesn't really matter what, if anything, is there in space, okay? So these formulas can be related to each other like this. E is equal to F over Q. So we have 2 formulas that are separate, and we can relate them to each other. All right? Now, we're going to go ahead, and we're going to switch to the first problem. And I'm going to give you guys a chance to solve it. So while we're doing this, if anyone feels like they have no idea what to do, feel free to raise your hand and I'll come circulate around and help you out. Okay, we're going to give about 90 seconds, and then I'm going to go over it. If you're not finished, I'm sorry about that, but I'm sure you'd rather see more of the material. All right, so we have 4 charges. Their values are Q, 2Q, 4Q, and 3Q. And we have a distance, D, on all sides. So, in order to solve this problem, we have to use what's called the superposition principle. So the superposition principle tells you that if I want to find the field at a point, I can just take the sum of all the fields caused by each of these three charges. All right? Now, this one, how much field does this exert at that point? Well, there's none. Yeah. So we're going to completely ignore the fact that there's a charge there. Field is independent of what's actually at that point because we're only talking about the point in space. So we're going to ignore that. We're only going to look at these three. So the field caused by this one, E2q, is equal to K2q over d squared, and it's going to be in the I direction. The field caused by this one is going to be K4q d squared in the j direction. And the field caused by this one, well, that's a little more complicated. So we're going to have K3q over, so how do we find the distance here? Well, we have to find the hypotenuse of this triangle. Okay? So the square root of d squared plus d squared, 2d squared, d radical 2, that's this distance. Okay. Does anyone not understand why I am having to use trig functions here? Because we're splitting the vector that is at an angle into x components and y components. Okay? So we're just going to add that, and all that. We're going to add it up. Oh, sorry about that. Okay, so when we sum the components, this is what we get. This is also what we get when we use a calculator to evaluate the trig functions. And this simplifies down to 5.91 kq over d squared. Okay, that's the magnitude. Now, the angle. Who knows how to find the angle? Well, we have to make a triangle. All right, and we have to use trig to find this angle, and it turns out that the angle 58.8 degrees. All right, Are there any questions about anything we did here? No. Okay. We're going to do this problem now. This problem requires you to use some of your Physics 1 knowledge, but that's no problem because everybody got A's in Physics 1 and knows exactly what they're doing, right? Question?
I'm sorry, going back to the last question. For example, if we were looking at 3Q instead of just Q, would like the I direction from 4Q be negative? Would you have
1 second, I'm sorry. Can you ask the question again?
So if we were looking at 3Q instead of just Q, if we were doing everything based off 3Q.
If we were looking at this point,
Yeah. And if like based off of 4Q, would that just be like a negative I direction?
well, so which direction is negative? When you're dealing with vectors, it kind of just depends on how you define one side to be positive and one side to be negative. But when you find the direction, right, so this angle is telling us that the field looks something like this. Over here at Q, it's going like that, okay? A little more up than it is to the right. And what matters is that we found the direction, right? Because positive, negative, that's like a binary thing. We're not dealing with binary things anymore when we're dealing with vectors. So if we were looking for the field here, okay, the field would probably be something like this. Okay, can you all see behind my head, or am I in the way? Here. The field would probably look something like that. And as long as you define the direction, like if, I don't know what this angle is, but suppose this is like 160 below the positive x, right? What we would do is we would say that. We would say the angle from the axis rather than calling something negative or positive. Alrighty? Alrighty, great question. Can I zoom in a bit? I probably can. Now, how I do that?
The 3 dots in the top right corner.
How's that? Can you see? Fantastic. Okay, we've got about 1 minute. All right, so the very first thing that I did was I drew a free body diagram because I know what equilibrium means. Equilibrium means that the net force on each body is 0. So what that tells me is that the up and down forces are going to cancel, and the left and right forces are going to cancel. This is on the negative charge, by the way. So I know that in order to find the upward component of the tension, I can use cosine of 10 degrees or sine of 80 degrees, doesn't really matter. So I'm going to say that T cosine of 10 is equal to negative mg. Okay? So mg is down. The upward component of the tension is up. They're going to cancel each other out. I also know that EQ is going to equal the force caused by the other particle, because these are negative and positive, so they're attractive forces, right? So F of 1, 2, and T sine of 10. Okay, that's the horizontal component of my tension. Are there any questions about that? No. Oh, yes.
You're saying that the angle between the rope and the, I guess the mass sphere is 10 degrees, but that's along on the top. Would it be 80 degrees if we're going from the sphere itself?
I don't fully follow. You think that I should be using 80 here and here?
Yeah, because if you're going by the sphere, the angle it's making towards between the angle between the string and the horizontal plane on the sphere is 80 degrees.
Well, so I could have chosen to use the 80, but so this is the angle that's 10, right? It's this one right here.
Yeah.
So if I do cosine, that's going to give me this side, right? Like this is cosine. So if this is tension, this is cosine tension, right? Because cosine is opposite, or sorry, is adjacent over hypotenuse, right? So this is going to be T sine 10. Does everyone agree with that? Is that correct? I'm sorry, I know that's obnoxious, I can't help it. So I use cosine to find the vertical component, cosine of 10. Now if I wanted, I could use sine of 80. That's the same thing as the cosine of 10, right? And I could do the same thing over here. I could use cosine of 80. All right, are we good on that?
Yeah.
Awesome, okay. So once I know that these sums are going to cancel out, well, I can compute some of these because I'm given an awful lot. So mg, what is g? Gravity. okay, negative 9.8 meters per second squared. M is given, however, it's given in grams. What's the base unit of mass? I'm not sure if somebody said something. I'm sorry, the drilling. So mass is 2 times 10 to the negative 3 kilograms, okay? So I can calculate that. I can also calculate, using Coulomb's law, the force between the two. So F1 of 2. This is going to be K negative 5 times 10 to the negative 8. 5 times 10 to the negative 8. Okay. Now, do I know the distance? I don't know it, but I can find it, right? Because I know this length and I know the angle. So I'm going to use trig to find this distance. Now, this is going to be 0.1 meters, okay, times sine of 10, right? Because opposite over hypotenuse times hypotenuse gives me opposite. Now, that distance. Is everyone with me so far? Any questions on that? Okay. Now, I think I need a calculator. All right. So I have that distance. So, to calculate t cosine 10, I'm going to use 2 times 10 to the negative third times 9.8. All right. Now I'm going to do divide cosine of 10 to get the tension. I assure you that is stressing me out as much as it is stressing you out. All right, so to find E, I plug in f of 1 and 2 and t sine 10. So t sine 10, I took this number, I multiplied by sine 10. I got that. Okay. And now I just have to plug this into my calculator, and I will get f of 1, 2. So who remembers what k is? To the 8th? Is it 10th or 9th or 8th? All right. So k times 5 times negative 5 times 10 e negative 16. I think I typed that in wrong. Okay, that's a little more right. And now I'm going to divide by this. Now, because EQ is equal to f of 1, 2 plus t sine 10, I'm going to divide by Q. All right, and I'm going to save a little bit of time from you guys watching me plug stuff into a calculator. But the answer that we get is 443 kilonewtons per coulomb. All right. Raise your hand if you got the same answer that I got. Raise your hand if you finished the problem but you got a different answer. Okay. Okay. Raise your hand if you have any questions. Yes.
Your equation under EQ, what is that equal to?
This? That's f of 1, 2. So that's the force from one charge onto the other charge. Okay, because these are the charges. KQQ over R squared. This is Coulomb's law. Okay, sorry that wasn't clear. All right. Yes. 4.43 times 10 to the 5th. Question.
You made the three diagram, the three-bar diagram was because of those in respect of the negative part, right?
Yes. All right. Are we ready to move on? Okay. So, the questions that we just solved were based around point charges. However, not all of the charges that we're going to be working with are going to be centered at a point. Sometimes we're going to have to deal with charge distributions. So there are a couple of formulas that you really need to know. So when we talk about charge density, we have linear charge density. All right. This is coulombs per meter. All right. Or Q over L. Okay. we have surface charge density, right, which is Q over A, which is coulombs per meter squared. And we also have volume charge density, okay, which is coulombs per meters cubed, or Q over volume. Pretty self-explanatory, but if you see these symbols, it's important that you know what they're talking about. So, we're going to do a problem that requires calculus. Yay! A thin ring of radius r carries a uniformly distributed charge Q. That is the total charge. What is the electric field at a point P on the axis perpendicular to the plane of the ring? I'm going to draw a picture for you so that you know exactly what the question is asking. So, at this point above the ring, what is the electric field? If you're finished, go ahead and stare at me so I know that you're finished. All right, so the first thing that we have to recognize about this problem is that field is a vector. We knew that already. But what that means is that this point over here, when it exerts a field, it's going to be at an angle like this. And this point over here, when it exerts a field, it's going to be at an angle like this. So what we notice about this is that all of the sideways field is going to be canceled out. So the field's total direction is just going to be up. And what that means is we're only going to have to bother to calculate the upward component of the field. Okay? So we start with the knowledge that E equals KQ over R squared times R hat. And the knowledge that lambda equals Q over 2 pi R. Now that comes from the fact that lambda equals Q over L, but we know how to calculate the length of a circle. It's 2 pi R, it's the circumference of the circle. Okay, so far we don't have numbers for these things, but we have known quantities that we can substitute in. Okay? We don't actually know what the angle is, but if we know the position of P and we know the radius, we can find the angle. Okay? Cosine theta is equal to height over radius. Excuse me. Over little r, which is the distance from the ring to the point, and that distance is h squared plus r squared. That's the Pythagorean theorem. All right? We have no idea what this distance is, but what we do know is h and r, so we can just use an equation instead of actually using this distance. That's what we're going to do. So we're going to need to integrate across the length of the circle and add up all the field. So the integral of dE from 0 to 2 pi. We can't just integrate that. We have to do a substitution. K. So now r squared, right? If this is r squared is h squared plus big R squared. And Q is going to be lambda. All right? Now, since we only want the upward component, we're going to use cosine of theta. This is the same thing as writing this. No. The good news is that we can actually pull out basically everything that's in here because these are not actually changing with respect to position. So what we're going to end up getting is this. KH lambda over h squared plus r squared to the 3 halves times s from 0 to 2 pi. Okay? Now when we use the fundamental theorem of calculus, that tells us that the integral from 0 to 2 pi is equal to f of b minus f of a. When s is 0, the whole thing is 0. So we just plug in 2 pi for s, and that gives us our final answer. All right. Are there any questions about that? Quick poll. Raise your hand if your professor is Dr. Dubé. All right. Raise your hand if your professor is Kostas. Okay. So you guys have to do calculus, right? All right. So the next thing that we introduced in this course is the topic of flux. So basically the purpose of talking about flux is to help us describe what field does in space. All right, so we have a couple of different formulas that describe flux to us. So flux, it's written like that, was originally defined as the field times the area times cosine theta, where theta is the angle between the normal vector and the field. Okay? So if the field is not going straight through the surface, the flux is actually going to be smaller than if it were. However, we also learned another formula for flux that actually turned out to be a really, really important formula. This is one of Maxwell's equations. Okay? It is the first of 4 equations that we learned this semester that basically summarize the entire class. Okay? And this is called Gauss's law. So Gauss's law is another way to measure flux, but it doesn't apply all the time. The important thing is knowing when we can use Gauss's law and when we can't. So Gauss's law is designed to tell you about this. If I have a charge, Q, and this charge is enclosed in some kind of surface, okay, then I can use Gauss's law to measure the flux through that surface. Gauss's law tells me that flux is equal to Q enclosed times what? A constant, a super simple constant that never changes. You only need to know one quantity to calculate the flux. But this only works for an enclosed surface that actually has charge inside of it. So over here I drew a little sheet that has the flux moving through it. That's not a closed surface, so we can't use Gauss's law to talk about that. It's not meaningful. So one of the tricks is just remembering when one law applies and when the other law applies. So if I have right, a surface like this, and I've got flux coming out. And I've got flux going in. Okay. If I tell you that the charge is somewhere over here, what that tells you is that the net flux through this surface is 0 because the charge is not inside. 0 over constant is 0. Okay? The reason for that is that the normal vectors on these shapes goes like this. This normal goes out. This normal also goes out. Normal vectors on the surfaces of shapes always go out from the shape. So here, cosine is 0, cosine, or theta is 0, excuse me, and cosine of 0 is 1. But here, theta is 180, and cosine of 180 is negative 1. So whatever the flux is here, it's the same but opposite from the flux here, negative and positive, and they're going to cancel out. Okay? So I have a problem for us to do. If I can get the computer to work, then we'll do a problem. 1, 2, 3. Can you read that? I can make it bigger. All right. We ready to go over it? All right. So, this problem actually kind of has a trick question component to it. If I can get it to show up on the screen. There we go. So, there's my diagram. Now, I'm going to use Gauss's law to solve these problems. Okay? So, the first radius is inside the inner ball. So, this is kind of a trick question. The answer is 0. Okay? There's a rule that we know that tells us that the field inside of charged conductors is 0. Okay? So E is 0. Now, if we know that rule, we can go down here to part C, and we can notice E is 0. All right? Now, we actually have to solve something for B and D. There are two ways you can do this. You can, if you want, use that E equals KQ over R squared, or you can use the fact that flux is equal to Q over epsilon, which is equal to E times A. Now, we don't need to use the cosine in this case because the cosine is 0, sorry. So cosine theta is 1. I'm going to do this, I'm going to use this way, okay? So if I have Q, that's 8 times 10 to the negative 6 coulombs divided by 8.85 10 to the negative 12 equals E times 4 pi R squared. Okay. So we're going to divide by A. We're going to have 8 times 10 to the negative 6, 8.85 times 10 to the negative 12, multiplied by 4 pi 0.03 squared. Okay. And that's going to give me 79.9 per Coulomb. Okay. I'm not going to make you watch me type that into a calculator. I trust that you know how to type stuff into calculators. But I'm going to go ahead and I'm going to do part D the other way, just so you see the both ways that we can do it. And you can judge for yourself which one you like better. I hope you choose this one. I think that way is better. So if I use KQ over R squared, I have 8.99 times 10 to the 9th multiplied by 4 times 10 to the negative 6. Now, if you're wondering where that came from, if I have 8 positive and 4 negative, that leaves me with 4 positive. Okay, I just canceled out the positive and negative to get the net charge. 0.07 squared equals 7.34 times 10 to the 6 Newton per Coulomb. All right. Are there any questions on that problem right there? Yes.
Why was
The
the electric field 0 at 4.5?
electric field is 0 at 4.5 because this outer shell that is solid and has thickness goes from radius 4 to radius 5. 4.5 is inside the shell. Okay?
How did you know that wasn't stated in the problem?
How did I know?
Why wrote 4 as a 5?
Oh, yeah. The problem tells you the radii of all 3 of these radii. So the inner ball has a radius of 2 centimeters. Then the inner side of the shell has a 4. The outer side has 5. So 4.5 is roughly here. Okay? All right. No problem. All right. In the interest of time, I think I'm going to go ahead and go over this one. Is anyone still working that would be upset if I didn't let you finish? No? Okay. All right, so this one had another trick question in it. If r is less than d, if the radius of the circle is less than d or equal to d, we can use the formula Q enclosed over epsilon. If there is no charge enclosed, then the field is 0, or the flux is 0. Okay? Now, if it's larger than D, okay, all we have to do is we have to find out exactly how much of that line is enclosed. Okay? And we have a formula. I believe this is for the chord of a circle. Okay? We have all right. I am pretty sure this is for the chord of a circle. If you don't recognize this formula, it's geometry. So all we're going to do, quite simply, plug this into the Gauss's law. So lambda times length over epsilon, okay? Because remember, lambda is Q over L, so Q equals lambda L. All right, so that one, not very long, okay? In the interest of time, I am going to skip the next problem on Gauss's law. I hope that that will not hurt your feelings, but we are kind of pressed for time. So the next thing we're going to talk about is what's called electric potential. So we have this thing called a volt. Now, a volt is actually, well, the formula looks pretty similar to the formula for field, but there is a very important difference here, and that is that electric potential is not a vector. Electric potential is a scalar. So, when we go from E to V, what we're doing is integrating E over some path. Okay? So electric potential is kind of like saying, if I have some plates, and I have field going like this between those plates, if I want to find the potential difference between these two plates, I'm going to just add up a little bit of field here plus a little bit of field here. I'm just going to add up all these little bits of field along the path. And that sum of all the field is going to give me my potential. Okay? And it is not a vector because it is not actually a real thing in space. It's a sum of real things in space. Okay? So we're going to do a problem, and it is going to be a pretty fast and simple problem because scalars are so much easier to deal with. I think before we do that, we're going to mention one thing. So field has energy within it, okay? That's kind of why we talk about potential, and that's kind of why we talk about field, because when we have some charges that are separated, there's a field between them that functions a lot like potential energy when we have something floating above the ground. So we have a formula for the potential energy, okay, negative work, KQQ over R, right? You see these are very similar equations. V equals U over Q. So they directly relate to each other in the same manner that field relates to force, okay? But these are also both scalars. So I think we're only going to do one problem on potential in the interest of time. It's not a very difficult concept, I don't think. Remember to stare at me when you're done. Okay, so I have a triangle. I have a distance here of 4 centimeters, a distance here of 2 centimeters. I have a negative Q, and a positive Q. And it's asking me to find the potential at this point right here. All right. So I happen to know that half of 2 is 1. So this distance right here, 1 centimeter, 1 centimeter. And we have to find this distance as well. So if I have a triangle 4, 1, okay, I know that 1 squared plus something squared equals 4. Okay. 1 squared plus a squared equals 16. A squared equals 15. So a is roughly 3.87 centimeters. Okay. Now, once I've calculated these distances, which was not that difficult, I'm just going to plug them into this equation. It's because these are scalars, they're going to add directly, and we don't have to think about cosines or anything like that. So we're going to say 8.99 times 10 to the 9th, 7 times 10 to the negative 6. And then we're going to have this radius, this radius, and that one. So notice these two are negative. That's just because these are negative charges, right? This is a positive charge, so we're going to add that. And when we calculate this, what we get is V equal to negative 1.1 times 10 to the 7 volts. All right. Are there any questions on that? Yes. So this is over R, right? These are the radii. I factored out K and Q from the 3 equations, right? Because this is V1 plus V2 plus V3. And now these are negative because these two charges are negative. So this one and this one ends up being negative. This one is this one. It's at the top. It's the biggest distance, but it's also a positive charge. Does that make sense? All right. So we're going to move on from potential, and we're going to talk about capacitance. So a capacitor is what you get when you have some plates and they have charge. We're going to have Q and negative Q, all right, on each of these plates. And the capacitance is basically a quantity that tells you about how much charge these things can hold. So the first formula we actually learned about capacitance that's pretty easy to forget because we don't end up using it is this one. It's epsilon times area over distance. And what that's telling you is that the capacitance of a capacitor is dependent upon the geometry of the capacitor, right? So having a bigger plate means you can hold more charge. Bringing them further apart actually means you can hold less charge, okay? We have another formula for C, which is Q over V. And that's the one that we use when we start talking about circuits, okay? Now, briefly, I'm going to tell you what a dielectric is. So a dielectric is when I have my plates and I decide that I want to stuff them with something, okay? Something that the field can go through more easily than air, okay? So we have what's called a dielectric constant. It's kappa, okay? It's like a squiggly K. This also just depends on the geometry of the material. Generally, I would expect them to either give it to you or expect you to solve for it directly. There's no tricks there. And we replace, so let's write dielectric constant, all right? And we replace this in the formula like this. C equals kappa epsilon naught A over D, or epsilon A over D. So epsilon of whatever the dielectric is. Epsilon is our vacuum permittivity constant, okay? When we use a dielectric constant with epsilon naught, we get the permittivity of whatever it is we're talking about. That's what this new thing is, okay? Now, before we do a problem with this, I'm going to talk a little bit about resistance. So resistance, I'm not going to go into as much detail about what causes resistance because it's a little more complicated, but we have this formula. Okay? So, like capacitance, resistance is pretty much dependent on the geometry of whatever material you're using and also what material it is, right? So copper, aluminum, whatever material. So length, this is telling you how long the wire is. If it gets longer, there's more resistance. This is the area. As it gets wider, it's more easy for things to flow through, okay? And this, right here, resistivity, okay? Kind of like the dielectric constant, resistivity is a constant, all right? No tricks here. So, all right. I'm going to take a quick vote because we're running kind of short on time. Who wants to try a problem? Other option is who wants to hear me keep lecturing about things? Yeah? Okay. That's what we're going to do. So the next thing that we're going to talk about is we're going to talk about current density. Okay? So current density, we use J, and it depends on sigma times electric field. What is sigma? Sigma is the conductivity, which is actually just 1 over resistivity. Okay? So again, not that complicated. Current density. And from this equation, we have this. all right? Number of charge carriers, charge of charge carriers, distance, time, okay? And if we plug that into this equation, we get this. We have drift velocity. We have the charge of a charge carrier and the number of charge carriers. And from this, we get this equation. All right, it says nave. And this is the equation from which we derive the concept of electric current. All right, A right here, this is the area. It's the area of the wire. So all we have to do is we have to take the current density, multiply it by the area, and we get current. So now that we know what capacitance, current, and resistance are, we can do circuits, which is probably what all of you guys are here for. Okay? So let's talk briefly about Ohm's law. So Ohm's law tells us two things. Ohm's law tells us that V equals IR. This is potential, current, resistance. It also tells us that C equals Q over V. All right. This is for capacitors, charge, potential. We're going to talk about how we add resistors in series and parallel, and capacitors in series and parallel. So, if I have two resistors, remember that we said resistance is given by resistivity length over area. There's a length, there's another length. This is the same wire, so we get to assume that the resistivity and the area of the wire is the same. What that means is, if I have two resistors in series, and I have a length of L and another length of L, this is exactly the same thing as if I had one big resistor of length 2L. Okay? It's kind of like taking this wire right here and just getting rid of it. Just removing it and bringing them close to each other. So having two resistors in series is exactly the same as having one big resistor, and that's why we add them directly. Okay? There's a similar idea with capacitors. These capacitors are in parallel. Capacitance comes from constant A over D. Now, we're going to assume that these capacitors have the same distance between them. Okay? Imagine that I were able to take these capacitors and just push them together until they touch. It would look like this. Okay? This is not functionally any different than the original two capacitors. What that tells me is that capacitors in parallel add directly. So I'm going to write that. Capacitors in parallel add directly. Resistors in series add directly. Okay? The other way that we add is inversely. So 1 over RT equals 1 over R1 plus 1 over R2 dot dot dot. 1 over CT equals 1 over C1, 1 over C2 dot dot dot. So this is how we add capacitors in series and resistors in parallel. There's not really an easy metaphor for that one, but if we know this, we just know these are the opposite. So it should be easy to remember which is which when it comes to adding in series and adding in parallel. Okay? So I'm going to talk about Kirchoff's laws, and if we do have time, we are going to do a problem of this because this is very important. But we have two rules. For junction rule, which tells you that the sum of the current into a junction is equal to the sum of the current out of a junction. Right? Looks like this. So I1 is going into the junction. I2 and 3 are going out. That means that I1 equals I2 plus I3. Not very difficult math. More important so that you know how to use it and when. Then we have the loop rule. Total potential in a loop is 0. Okay? So that means if this battery is 10 volts, we have some voltage here, V1 plus V2 equals 10, or 10 minus V1 minus V2 equals 0. Now, does anyone have any questions on that so far? No? All right. I think circuits are worth doing a problem for. All right. It's a Kirchoff's rule problem, and there's two batteries. I'm going to tell you, the first time I took this class, well, I mean, the time I took this class, because I got to sit through it as an SI leader, but this was the only topic that I didn't get. I got into the test, and there were two batteries, and I was just like, I have no idea what to do. Okay? So if you feel like that, we're going to know what to do on this, okay? And we're going to use Kirchoff's laws. Take a moment to try it, but not too long. I'm going to go over this before we leave. I think it's very important. Okay. Now, okay. So, I drew out my circuit, and the very first thing I did was I took the series resistors and I added them together. Okay? Because why make this hard when you can make this not hard? Make it less hard. So, then we're going to have three equations. We have to make a loop here, a loop here, and another loop that's all the way around. So we know that the potential in a loop adds to 0. So if we presume this loop to go this way, we're going to have 12 minus 4 times whatever that current is, minus 6 times whatever this current is, minus 4, because we're going the wrong way through this battery. That's why we're going to subtract, okay? It's going to act as a resistor. Now, for this little loop, we've already defined I1 is going that way. We've defined I2 is going that way. We're going to need I3. That's going to go up. So we have eight I3 is going to be negative. We're going to have 6 I2. And then we're going to have that. Now, this doesn't make a ton of sense when you first look at it. You're like, David, how can this add to 0? These are all negative. Well, the reason that this is going to work is that this value, I2, it's going to end up being a negative value. We had to be consistent when we set this to some value. We have to use the same direction both times, but the current probably actually goes up. Okay? So this is just something that happens when you use the loop rule, and you'll get the answer in the end. Now for this one, 12 minus 4I1 going the wrong way through 8I3. Okay? Now, we have I1 plus I3 equals I2. That's the junction rule. Okay? It's off the screen a little bit. The junction rule lets us make that equation. Now, I'm not going to solve this because systems of equations can take a long time, and I trust that you know how to do that. But the important thing is the setup and the fact that you can substitute in for these I variables to reduce the number of unknowns. Are there any questions about that? No? All right, great. Okay. I'm going to go ahead and hand out for you guys some question. What's up?
That green that you had?
The green?
Yeah. That's like the third equation that we got.
Oh, the big loop? Yeah?
How did you know how to do that?
How did I know how to do that? What did I do? So what I did was I ignored the central line entirely, okay, and I traced around, all right, 12, 4I, and now you're probably wondering why I put plus. Is that what's giving you a hard time?
You're going with the current, right?
Well, when I did the second loop, I defined I3 as up. Okay, so I think some of the professors do this thing where they write little pluses and minuses on all of these. I'm going to be honest with you, I don't know exactly what it is they do, so I don't want to risk doing it wrong, all right? But you write a plus and minus to say, okay, well, we go down in the second loop, okay? Now, when I do the third loop and I'm going through that, I already defined I3 as up. I don't get to just change it, okay? So the normal thing to do is subtract, okay? So I had to do the opposite. I had to add. It's no, it's not a clockwise counterclockwise thing. So the fun part about Kirchoff's laws is that I can draw my circles wrong and it'll still work, right? Because we don't know necessarily which way the current is going, so we kind of have to guess. And if we get a negative number, then we drew it backwards and we switch the sign and we're done. Okay? All right. So I have some surveys for you guys. If you will take them and fill them out, and you can say David was helpful or he was not very helpful. Either way, I want your feedback. I'm going to pass these out. Sorry about that. I'm going to try not to step on any more students. All right, and I've got a few more things to say before I leave, but you can fill these out while I talk. Can you do me a favor and pass these behind you, and can you pass those over? Thank you. Did I give you too many? Sorry. Okay. So Kirchoff's laws. That is that. We still have a little bit of time. So I definitely want to introduce magnetism. Okay. So the very first law that we covered in magnetism is called the Biot-Savart Law. Okay, which is mu naught I over 2 pi r. Okay, this is the analog of Coulomb's law. It's the analog of this. Okay, so the reason that this is an analog is that when we have a sphere, okay, with a charge, that charge radiates outward, or the electric field, excuse me, radiates outward like this. Okay, so if we want to find the field at a point at distance r, we know that the total field, that the total flux is given by the charge, okay, over epsilon naught. And so what we're doing is we're dividing by the surface area. Okay, that's why this is an inverse square law. We're dividing by the surface area of the sphere. Now, field in the magnetic sense doesn't work exactly like that, because if I have a wire, the field doesn't radiate outward in a spherical pattern. It radiates around the wire like this, okay? Radiates around the wire. So when we divide by 2 pi r, all we're doing is dividing by the circumference of that circle, okay? So I have one more problem that I want to do. This is a calculus problem. This is going to be the last thing we do. Yep, here it is. So I'm going to give you a wire. It has a current I. And I want to be able to calculate the field through this square. Okay? And the field we know is doing this. All right, around the wire. So we're going to add up all that field. We have a width and a length. And we have this distance right here. It's going to be D. Okay. Who here upon seeing this problem feels like they know how to do this? Yeah? Good. Good. I don't have enough time to have you guys try to solve the problem, okay? But I will do it for you. So the flux through this little square is going to be B dot dA. We're going to integrate from D, should be A, to A plus L. So we're integrating along this path. We're splitting this up into rectangles, okay? The reason that we can do that is that the field changes with respect to L, but not with respect to W, okay? It stays the same with respect to W. So now we have mu naught I over 2 pi W dr over R, okay? This is just the Biot-Savart Law. W is a constant we're multiplying by. We're definitely going to pull that out. So we're going to integrate dr over R from A to A plus L. All right? Now, the integral of 1 over x is what? Yes, very nice. So we have mu naught I W over 2 pi ln R from A to A plus L. Now we're going to use the fundamental theorem of calculus. We're going to get mu naught I W over 2 pi ln of A plus L minus ln of A. And we are going to get the final answer, flux mu naught I W over 2 pi ln A plus L over A. All right. Does anyone have any questions on how we did that? I'm sorry I couldn't give you a chance to do it yourself, so I hope that you were able to follow. I find that it's a little easier when you've had a chance to think about it first. But we are pretty much out of time. I appreciate you guys. Do me a favor, just leave your surveys where you're seated and I will pick them up. Don't worry about it. And I wish you all the best of luck on your exam.